Good morning, ladies and gentlemen. Professor Michel Shea and I are greatly honored for introducing Professor Richard Schrock at the Department of Chemistry, MIT, who received the Nobel Prize in 2005. One thing I have to tell you, even though it is a personal matter, Professor Schrock's mother passed away last week, but he has to come to Korea to deliver his plenary lectures. I'd like to express our deepest condolence to Professor Schrock. Now Professor Shea will introduce his career briefly.
So good morning, everybody. So it is a pleasure for me to introduce Professor Schrock. I will do that rather briefly because Professor Schrock is very well known. So Richard R. Schrock received his PhD degree in inorganic chemistry from Harvard in 1971 under the tutelage of John Osborne. After spending 1 year as NSF postdoctoral fellow at Cambridge University, working for Lord Jack Lewis, and 3 years at the Central Research and Development Department of the DuPont Company in Wilmington, Delaware, he moved to MIT in 1975. He became full professor in 1980, and Frederick is professor of chemistry in 1989. His interest spanned three main areas of research. So the research area of longest standing interest concern complexes that contain metal-carbon multiple bonds, usually alkylidene complex, where the metal is usually tungsten of molybdenum in its highest possible oxidation state. And the primary goal is to synthesize and characterize complexes that are catalysts for the metathesis of olefins and that have predictable and controllable activities. A second area of research concerns the reduction of nitrogen in a well-defined manner, and the ultimate goal being activation and reduction of dinitrogen using protons and electrons. And the last area of research concerns the controlled synthesis of specialty polymers with alkylidene complex catalyst by either ring opening metathesis polymerization of cyclic olefin or by cyclopolymerization of heptadiene to yield polyene. So Professor Schrock got so numerous awards that it will take me too much time to cite them all, culminating in 2005 by the Nobel Prize, shared with Yves Chauvin and Robert Grubbs for the metathesis of olefins. So it is a very great pleasure to be able to be to listen to this lecture, and Dick, the floor is yours.
I want to thank the organizing committee for getting me to Korea. It's my first trip to Korea, my first lecture in Korea ever, so I'm very pleased to be here. I had the opportunity to choose between two of the subjects that Professor Che mentioned, the reduction of dinitrogen and metathesis of olefins, and we have some very recent exciting results in the longer standing area of olefin metathesis, so I thought that is what I would talk about today. Can you manually move the slides? I don't seem to be able to up here. There we go. Okay. So this is an old reaction, over 50 years old. I'm sure most of you have heard of it. Olefins are essentially chopped in half. So it was discovered by a man named Herb Eleuterio at DuPont, and I was at DuPont from between 1972 and 75. Although I didn't meet Herb, he was still there at that time, but he did this in 1956. And what it is simply a reaction between an alkylidene and an olefin to give a ring, and then that ring breaks up one way or the other and carries out this scrambling reaction. So between the time at DuPont when I discovered some new alkylidenes of tantalum in 1986, so a period of 12 years, I developed what I call well-defined catalysts for this reaction, something you can put in a bottle, you can do crystal structures of, and do kinetics, and so on. Bob Grubbs, who shared the Nobel Prize, as you heard, created ruthenium catalysts in the early 90s that were less sensitive to air and water and preferred by many organic chemists. The classical catalysts for this reaction, many of them heterogeneous in fact, would not tolerate functionality, so it required the development of these well-defined systems in order to use them the way I'm going to tell you about today. So there are many variations of the metathesis reaction. The simple one that I showed on the first slide is not very useful. This one in which you evolve ethylene and make a coupled olefin, that's the next more fancy one, if you like. There's a cross metathesis to make the cross-coupled product. Strained olefins can be opened up to give polymers, as was mentioned, things like norbornenes, polynorbornenes, and norbornidines, and cyclopentenes, and so forth. And you can make rings. This is an important development in the area of organic synthesis, since many rings are of importance in natural product synthesis and the like. And then you can ring open, cross, metathesize them. And on the next slide, I show the ene-ine reaction. So it's an acetylene reacting first, followed by an olefin to give rings again. Acetylenes can be polymerized. These 1,7-heptadiene, 1,6-heptadiene polymerizations were also mentioned, and there are many more applications. I don't want to bore you with all of them, so I just showed you a few examples here. So the catalyst that I developed between 74 and 86, the first one was a molybdenum, was actually a tungsten catalyst, but they all have this general architecture. 4-coordinate, so they are electron efficient, as we call it, 14 electrons, so there's 2 coordination sites on the metal. For the olefin to bind, just 1 is needed, of course, to make the ring. The imido group is like the alkoxide, variable, and that's very important because you can choose many different electronically different and sterically different imido groups and many different alkoxides, and I'll show you later. These alkoxides, of course, can be bound to surfaces, and so you can actually create heterogeneous catalysts derived from these species. All of these have to be bulky, and the real reason is to prevent bimolecular decomposition, because these alkylidenes are decomposing in solution all the time, especially when the alkylidene is very small. And that's really the challenge, to control the decomposition of alkylidenes, which are really part of the metathesis process. The metallocyclobutane is the intermediate, various structures. You make products, and then if you ever make a methylene, the smallest, of course, is especially liable to decompose bimolecularly. So that's one significant decomposition pathway. This you could control by putting a catalyst on a surface, as I'll show later. However, there is a second decomposition pathway that takes place from the metallocycle, and that's a rearrangement of the metallocycle to an olefin. For example, the unsubstituted metallocycle here, by a beta hydride rearrangement, rearranges to propylene. So the alkylidene is destroyed in each of these processes, and therefore the reaction slows down and stops. Remaking an alkylidene in these sorts of systems is one of the remaining challenges in the area. This is, of course, a unimolecular reaction in metal, but it seems to be catalyzed by ethylene now. Very recent results suggest that it's catalyzed by ethylene and other olefins. So the very olefins that you need to carry out the reaction lead to methylenes and also catalyze the decomposition of metallocycles. The synthesis of the catalysts of this type are shown here. So it's a 3-step synthesis starting from molybdate. You put the amido groups on first, you put the alkyl groups on next, neopentyl or neophyl, and then you take off one of the amido groups, make an intermediate, and lead to a bistriflate species, which is then the precursor to bis-alkoxides, and I'll show you today other species by displacement of the triflates. So all of these species are air and moisture sensitive. They are highly active and therefore quite reactive towards air and moisture in many functionalities. So the message is that you can control reactions very, very finely by varying the amido group. Here are 8 different amido groups. There's a huge steric component and a very significant electronic difference between many of these, so that all changes the reaction significantly. And then many alkoxides, and we become particularly interested in asymmetric reactions, reactions involving enantiomerically pure catalysts, and those are often, as in many asymmetric catalytic reactions, they often involve bidentate ligands, and biphenolates and binaphthalates and the like are perfectly suited for that in this particular type of compound, pseudotetrahedral species. But again, there's a huge steric component and significant electronic differences. If I have time, I don't know if I will, I can point out some differences in terms of polymerization activity between this biphenolate and the one with CF3 groups in place of methyl groups. Completely different activity. So these are complicated reactions, even though they look simple, but they can be controlled very finely. I just want to show a couple of asymmetric reactions to give you an idea about what we're talking about. So here's an enantiomerically pure catalyst with one of these biphenolates on it, and we can do what are called ring closing, actually desymmetrization reactions. So this double bond reacts with this one first, makes the initial metathesis product, and then the ring is formed through attack on one side or the other to make this rather a small, easily made 5-membered ring. Now the object, this is several years ago, was to determine what we could make and how well we could do it in terms of EE. You can see the EE is quite high, 99%. It's essentially one product in this case with very little catalyst, no solvent, and it's over in a few minutes at room temperature. The products are, of course, this olefin in this case, where that's a methyl, it would be propylene. So very clean reactions, fast reactions often, and asymmetric, creating one enantiomer as shown here. If you want to carry out another reaction, you need a different catalyst, or you may need a different catalyst. So you have to pick and choose which one you need through experimentation, just the old-fashioned way by just choosing a catalyst and trying it. And this one, in this case, carries out this reaction to make the 6-membered ring. Now, these are very simple substrates, very simple products. I'll show you some more sophisticated ones later on. Rings containing nitrogen are more important, alkaloids and the like. So we moved to nitrogen a few years ago. This was work by Sarah Dolman a few years ago. And again, you have to use the right catalyst. This one works for the 7-membered ring, essentially enantiomerically pure, very high yield. And to make the 8-membered ring on the next slide, you need a different catalyst, the dichlorophenoamido. So you need a catalyst that will do the job, and you have to find out, of course, which one that is. So catalyst variations are the answer, but there are hundreds of catalyst variations just by multiplying together the number of amido groups and alkoxides and the like. And we wanted to design a way to make catalysts in situ so we could do rapid throughput, if not actual combinatorial type evaluation of catalysts for various reactions. So we decided to look at X groups on the metal that could be replaced by protonalysis with an alcohol. So some alcohol or diol would replace the X group to give HX, and we chose X as neopentyl, so an alkyl group, and diphenylamide initially. So that would give neopentane, which should be completely innocuous, and diphenylamine, which may or may not interfere with the subsequent reaction of the bis-alkoxide, which initially was what we wanted to make. So we found that, in fact, we could add 2 alkoxides to diphenylamidose species and make bis-alkoxides, but mononeopentyl species were the only species that could be prepared from dineopentyl precursors. So there were some troubles with the synthesis of these materials, these compounds, and then we hit upon the idea of using pyrrolides as a leaving group. So this pyrrolide is just the nitrogen analog of cyclopentadienide, C5H5-. It's an old ligand in chemistry. People were interested primarily in it as an A-5 ligand, like cyclopentadienyl can bind, not as a leaving group. We were interested in it as a leaving group. So we found out that these reactions with the bis triflate were very smooth, clean, high yields, and the products were highly crystalline and easily isolated, and you could make many of them in wide variation, different amido groups and so on. And that's what we were then became involved in. And we found that, in fact, bis pyrrolides reacted very slowly with olefins. The metal is simply not electron rich enough. The structure of the parent pyrrolide isn't what I showed in the previous slide. It's actually more complicated. It actually has this piece at one end. You see A to 1, A to 1, as shown here, and at the other end, A to 5, A to 1, A to 5, A to 1, with this nitrogen lone pair binding to that molybdenum. This comes apart right here to give these 2 pieces, so that equilibrium is fast, this equilibrium is fast, and so what you see by NMR, for example, these are obviously diamagnetic, you're just a lot of broad signals, so it doesn't look very nice at room temperature, but they are very nice pure compounds. At low temperature, you can see exactly what the structure is just because you slow down these processes. If you substitute the pyrrolide, 2,5-dimethylpyrrolide, for example, reactions are again smooth, and then you get an A to 5, A to 1, 18 electron species. Here's the structure of an adamantyl imido A to 5, A to 1 species. Again, fluxional. These 2 pyrrolides interconvert, and you proceed through, presumably, A to 1, A to 1, 14 electron intermediates. All of these alkylidines are syn, meaning this substituent points towards this imido group. The other isomer is anti, which we don't see in these particular compounds. You can force the pyrrolide to be A to 1 if you put a substituent in the ortho position like this mesotyl group that then makes A to 5 binding virtually impossible. So this is now for the mesotyl substituted pyrrolide, A to 1, A to 1, 14 electron, syn as shown. 14 electron, I keep emphasizing because that's likely to be more reactive in terms of reacting with an alcohol to give a bis-alkoxide. You can go to other types of pyrrolide-related species like indolide, this benzyl pyrrolide, if you like. That's A to 1, A to 1 also. So we were very pleased to find that these pyrrolides, I wouldn't be telling you unless they did, react very nicely with alcohols. And so you can make bis-alkoxides or biphenolates or binaphthalates in wide variety, sometimes very rapidly, especially from the parent pyrrolide complexes, and essentially quantitatively. Now, it's interesting to note that pyrrole is the product of a proteinalysis reaction, and pyrrole is close to benzene. It doesn't bind to a metal at all. So it turns out, I'll show you evidence that it does not interfere with any metathesis reactions that we've seen so far. So these reactions, making the bis-alkoxide or diolate, can be fast, especially for the parent. More demanding, sterically demanding pyrrolides like dimethylpyrrolide react a little bit more slowly. Pyrrolinene complexes are the likely intermediates. What's a pyrrolinene? A pyrrolinene arises from protonation at that carbon. So that is, of course, an isomer of pyrrole. If this comes off the metal, then it rearranges to pyrrole, and that's the overall reaction. We've actually isolated a couple of pyrrolinene complexes and shown that they do, in fact, that they do in fact exist. For example, this tungsten species reacts with this barf salt of dimethylaniline to deliver a proton to the alpha carbon of dimethylpyrrolide, and here is the pyrrolinene, in fact, added to the metal. This proton was located, and when THF displaces that pyrrolinene, you get dimethylpyrrole, and then this cationic THF complex. So these pyrrolinene complexes do form, and we think they're probably formed in many cases. So I just want to show you, first of all, a number of things, but first of all, I want to prove to you that you can make these catalysts in situ just by adding the diol or the biphenol or the binaphthol to the bispyrrolide, and that they do the same in solution or behave the same way in solution, even though pyrrole product is present, as the isolated catalysts. So this is the nomenclature. This is a diisopropylphenylamido bifen species. You don't really have to memorize this. All I'm doing is, for this particular reaction, going to compare the yield, conversion, and so on, and EE for 3 isolated catalysts with the catalyst prepared in situ in the dry box. And you can see, I won't go through the figures, let's just look at the EE, that they are the same, 97, 98, 61, 60, 98, 97 for the in situ catalyst versus the isolated catalyst. So we decided to, in fact, do this in a Schlenk manner, not in the dry box. We made up sort of standard solutions, made up catalysts in situ as we needed them, and then compared whether these catalysts behaved the same after several days, weeks, and so forth in these flasks in a hood under nitrogen. So this same reaction is shown here with 3 different catalysts prepared in a dry box after 3 days in the hood, after 10 days in the hood. So this catalyst you can see in the dry box or in the hood behaves the same way, all in situ. This catalyst for this reaction, dry box, hood, all behaves the same way. This one all behaves the same way. Same EE, some differences in yield and conversion. So you can make these catalysts in situ and use them. Here's another example, different rearrangement, 3 different catalysts, in situ, dry box, hood, all the same results. Of course, these are not very good EEs. This one is, in fact, racemic, so it gives racemic product, but it shows you that, in fact, these reactions all behave the same. And then so that's good news. So now you can make these catalysts in situ. You can make biphenolates, binaphthalates, everything. We've published 35 or so papers, largely in collaboration with Amir Hoveda at Boston College on asymmetric reactions. And then we asked the question, what about monoalkoxides? And they are obviously likely intermediates in a reaction in which you replace 2 pyrrolides. You should be able to isolate, or perhaps could isolate, the monopyrrolide monoalkoxide. Now we know bisalkoxides are quite reactive species. Bispyrrolides, as I mentioned, are very poor in terms of reaction with olefin. So we thought that the monoalkoxides would be somewhere in between in terms of reactivities. You can make these monoalkoxides. Sometimes they are largely the only product. Sometimes they are a high percentage of the product. And we call them monoalkoxide pyrrolide species, MAP complexes. And one thing you note about them is, you should notice, is that they are asymmetric at the metal. So there are 4 different groups bound to that central metal, pseudotetrahedral, of course. The alkylidine will change, but there's no ligand on the metal that is not covalently bound. All ligands are covalently bound to the metal. So you can isolate these monoalkoxides, and crystal structures have been done, and there's nothing very surprising about any of the structures. A little bit surprising in some cases, like this one, where you have diisopropylphenylamido, diisopropylphenoxide, alkylidine, 8-1, 2,5 dimethylpyrrolide. So this is a 14 electron species. It could be an 18-electron species, that could be 8 of 5, but it's not, probably for steric reasons. These are all very, very crowded, generally very crowded metal complexes. One thing that we found out is early on is that although bisalkoxides of molybdenum don't carry out the E9 reaction in any controlled way, ruthenium does, we found that these monoalkoxides do carry out E9 reactions. For example, this very simple one where you make either a 5-membered ring or a 6-membered ring gives, in the case of 4 and 5, isopropyl hexafluoroisopropoxide, hexafluorotbutoxide, 100% of the 6-membered ring, which I call the beta addition product. So the initial triple bond adds to the alkylidine to put this substituent in the beta position. That leads to the 6-membered ring, and it's 100% beta addition product. The interesting thing is that ruthenium only gives alpha addition products as far as we could tell in terms of what's in the literature. So that is some bonus then for molybdenum. You can make products that ruthenium will not make. Here's another example. Now putting another methylene in the side chain, you can make then this alpha addition or beta addition product, 6-membered or 7-membered ring. And now there is not a selectivity as much for the beta addition product, but still 100% in these two cases, and then both alpha and beta in these other cases. And again, only ruthenium, or only the alpha addition product is found with ruthenium. And then we became interested in the possibility of controlling the chirality at the metal. Now this is a subject that goes back in inorganic and organometallic chemistry and catalysis for several decades. People have dreamed about the possibility of doing asymmetric reactions by virtue of the fact that the metal itself, the metal center itself is chiral, not that some adjoining ligand attached to the metal makes the metal chiral. It is chiral because of the arrangement of the ligands, 4 different ligands around the metal. Now, of course, when you make a monoalkoxides from a bispyrrolide, you have a mixture of enantiomers, it's racemic, but if you use a chiral alcohol, an enantiomerically pure alcohol, then you should make diastereomers. And so we became interested in making diastereomers and investigating their reactivity and using, therefore, the chirality at the metal center in the form of a diastereomer. And what we find, here's the first experiment a few months ago, very easy to make enantiomerically pure alcohol derived from camphor, adds to a bisalkoxide to give only the monoalkoxide as 2 diastereomers. 25% one, 75% the other. This has the S configuration. This has the R configuration, because if you do a crystal structure, you can see that the major diastereomer, the one on the right, has in fact the R configuration as shown here. Nothing very surprising about that structure. And then we decided to, well, let's try some reactions with these diastereomers, either as pure diastereomers or as mixtures. We found that in this case, this reaction, again, our sort of test reaction, was very, very slow, even at 55 degrees. Days were required for this reaction to go to completion. Both diastereomers initiate slowly and are obviously not very efficient in terms of ring closure. So you can now isolate the pure diastereomer. You can make various mixtures of diastereomers and test all of those as catalysts. So mixtures of diastereomers or the pure diastereomer, the major one, not the pure minor one. And it's a terrible, terrible result. That is, if you look at the EE of that product, 55 degrees, several days, the pure S diastereomer, the one that we didn't get the crystal structure of, the pure R diastereomer, what am I doing? That's a pure S, so 0% R. That's a pure S diastereomer, gives about 4% EE, and these various mixtures, this is now 75% R, gives about 18% EE. So pure R, the one that we couldn't get the crystal structure of, we got the crystal structure of the S, would only give about 20% EE. So a terrible, terrible start to this new area. Then we started to look at other alkoxides, and in particular, half-protected binaphthalates or biphenolates or bitetralins. Now these are, of course, in the diol or diolate form, or the very ligands that we've used to make asymmetric catalysts, hundreds of them in the past. We simply protect one half and use this as a monophenol, monodentate, enantiomerically pure alcohol or phenoxide. So again, this particular one, this is actually, they're very easy to make. This is actually a precursor. I think it's like 2 steps from commercial binaphthol, 3 steps if you count the hydrogenation. Very often these bromides in the 3 and 3' position are actually used as intermediates to things we have made, for example, a trisopropylphenyl in this position through coupling reactions. So these are intermediates in some of our known reactions to make biphenols and binaphthols and bitetrols. So this one is then protected with a T-butyl dimethylsilyl group here, and everything on this particular monophenoxide, or monophenol in this case, is important. We've tried hundreds of variations, and so there are literally hundreds of even this type of variation, and if you want to go into other alcohols, many more. Anyway, what we found is that this is a quite unsymmetric or dissymmetric type phenol. It's big. It adds to the bispyrrolide to give, now again, a mixture of 2 diastereomers, and now the major isomer is the S. The minor isomer is the R, and the ratio is 7:1. We've crystallographically characterized the S to show that it is the S. And we found that for different pyrrolides, you get rather different diastereomeric ratios. Instead of 7:1, for example, with tetramethylpyrrolide and many of the other species that I've shown earlier, you get different diastereomeric ratios. For tetramethylpyrrolide, you get a diastereomeric ratio of 35:1, so 35:1. And we were interested in, of course, whether those diastereomers do react in our test reaction, and either as mixtures or as the pure compound. And we find that, unlike the first case, they do, or at least this particular MAP catalyst, the second one that I'm talking about, does react as well as any other catalyst that we have of the biphen type, biphenoxide type. For example, with diisopropylphenylamidol and the original biphen ligand, 5 mol% in 20 minutes will carry out this reaction in 98% EE. The MAP catalyst now, instead of being more or less inactive, is about the same, 2.5 mol%, room temperature 15 minutes, 93% EE with the mixture of diastereomers, 96% EE with the pure S diastereomer. So presumably what is happening is one diastereomer is tuned to the extent that it reacts and the other one doesn't. At least that's what we're thinking initially. Now, alkylidines form during the reaction, different alkylidines, so they may or may not begin to interfere and to give presumably the opposite result from the one that we've observed. So it's a highly delicate tuning process. So let me show you some other examples, and we began to realize that these catalysts are special. They're highly reactive. They're not sort of halfway between the unreactive pyrrolides and the reactive bisalkoxides. They are, in fact, sometimes almost infinitely better, but certainly 100 times better in speed than bisalkoxides. So here are some other all-nitrogen-containing substrates, ring-closing reactions. This is the result for the best isolated biphen or biphenoxide or whatever it happens to be catalyst that we've developed for this reaction. And then this is the result for the MAP catalyst that I just mentioned. So the best catalyst for this reaction up to this point, 2 mol%, 7 hours, 95% conversion, 95% EE. pretty good, a little slow. The MAP catalyst, 1 hour. Same result, more or less, a little lower EE. So the MAP catalyst is about 10 times better for this reaction. Here's another one, rather difficult, bicyclic species is formed. Difficult to do that reaction. Dimethylphenylimido, bifen, is the best catalyst. 15% terrible, 24 hours, 30% EE. That's the best one we had ever seen. The MAP catalyst, 1 mole percent, 1 hour, 90% EE. So that's about 200 times better. Here's a substrate that is very difficult to, like all substrates having protons on nitrogen or oxygen, very difficult to close because that's a rather reactive proton. But in fact, with all asymmetric catalysts that we've tried before, we could not carry out this reaction, presumably for that reason. The MAP catalyst, for reasons we don't understand, in fact does carry out this reaction, 5 mole percent, 1 hour, 67% EE. Not a very good EE, but the fact that it carries out the reaction at all makes the MAP catalyst almost infinitely better than anything we've had before. I think just a couple more examples of how startlingly successful these MAP catalysts seem to be. Here's another reaction, very typical cyclic ether. The best catalyst, 5 mole percent, 6 hours at 60 degrees, 84% EE. The MAP catalyst, 1 mole percent, half an hour at room temperature, 60% EE. So these are very fast catalysts. Here's another example. Instead of 5 mole percent, 12 hours, 1 mole percent, 1 hour, 86% EE, 94% EE. So these are highly successful species, highly successful catalysts. The biggest surprise was this one here. There's never been in the literature any, what I would call a real synthesis of some natural product, something that's difficult to make, especially asymmetrically. No asymmetric synthesis, for example, of this species, which is obviously multicyclic alkaloid derivative called quebracamine. A woman in Amir Hoveda's group, Liz Saitley, developed a metathesis route to quebracamine that involved one of these desymmetrizations. The catalyst would react here and close on this vinyl group or that vinyl group, establishing that chirality, then through hydrogenation would give the final product. The only catalyst that worked in this reaction, this ring-closing metathesis reaction, was the hexafluorotebutoxide of molybdenum. 15 mole percent disaster, 12 hours, 98% conversion, 71% yield. But of course, it's not asymmetric. Every asymmetric catalyst we ever tried, all the molybdenum ones that we know of, and there are some ruthenium ones, and Amir Hoveda does work with ruthenium, so we used every catalyst we could find that was asymmetric, and that led to no conversion at all. The in situ made MAP catalysts now are strikingly successful, amazing. The dibromide one that I've been talking about, as a 7-to-1 diastereomeric mixture, 2 mole percent, 1 hour, 95% EE for that product. If you, in the 3 and 3' position, replace the bromides by chlorides, 5-to-1 diastereomeric mixture, you don't actually have to isolate the pure diastereomer, 1 mole percent, 96% EE. So for the first time now, we not only have some pretty impressive syntheses of a natural product, but we have catalysts that, for reasons that are not clear to us, completely clear by any means, are amazingly active. Well, this just shows that you can actually buy bistriflate from Strem, use Schlenk-type techniques, add the lithium pyrrolide to make the bispyrrolide, add the alcohol to make the monoalkoxide, and get the same yield conversion in EE that you do with the reactions I've been talking about, starting with the actual bispyrrolide itself. So what's going on with these new catalysts? And we saw a paper here. We collaborate with the Basset group and I in particular with Christoph Kopperay, and they collaborate also with Odile Eisenstein, who is a theoretician, and she came up with a reason, a possible reason, and based on calculations, an explanation for why these asymmetric at the metal species are so reactive and how that olefin attacks the metal. And what she believes is, this is the donor is a purolide, the alkoxide there is what, of course, the alkoxide, and she says that the olefin attacks the carbon-nitrogen-oxygen phase trans to the donor, whatever that donor is, in my case, purolide. But she did a more general analysis of this problem. And therefore, transition states and so on are lower for this forming a metallocycle and rearranging and reforming the olefin than if you switch the alkoxide and the donor over here. In fact, the bisalkoxide is the next best catalyst. So this is the best in terms of transition state energies and so on. This is the next best. This one where these two are switched is the next best, and the one that's worst and in fact very bad is donor-donor, and we know that. Pyrrolides, for example, or dineopentyl species don't react at all with olefins. So there is some electronic preference for the olefin attacking the metal in the way that we think it does in a bisalkoxide, but in a donor acceptor type situation, trans to the donor, which was a big surprise. We thought it would be the other way around. Distorted non-ideal structures, including metallocyclobutanes, are of course formed in these situations, and that's good too, because you don't want a metallocycle to be perfectly symmetric. You want it to be distorted, liable to break up and rearrange and form products. So they are inherently less stable in unsymmetric situations, unsymmetric at the metal. We recently got a crystal structure. This is by Smirana Mironescu in my group. And we showed that if we consider a trimethylphosphine, a substitute for an olefin, which is a stretch, but it's worked in the past, we find that in fact this hexafluorotebuthoxide diphenylpyrrolide trimethylphosphine adduct does have the structure shown, predicted by Odile Eisenstein. There's an equatorial alkylidine, equatorial amido group, equatorial alkoxide, and trans to the phosphine is the pyrrolide. So the substrate, this substitute for an olefin now, comes in trans to the donor, the pyrrolide. This is a very long bond, 2.55. So this is a very weakly bound phosphine, as you might expect, being trans to this donor. And she predicted that it is better to have an olefin bind weakly to the metal. You don't want substrates to bind strongly to metals. You want them to bind weakly. That enhances, in fact, their ability to go on to the next intermediate, in this case, a metallocyclobutane. The MAP catalyst, and this is the blown up structure of that one I've been talking about with two bromides in the 3 and 3' position. You show that you can see trans to this dimethylpyrrolide is this face where the substrate is going to come in, and that face is blocked pretty much by that bromide in that position. And in fact, this species does not form a trimethylphosphine adduct for that reason. There may be other reasons why these catalysts are so good, and one very simple reason is because they last longer, because methylenes, which are the most unstable intermediates formed in many of these reactions, the ones I've shown you in particular, are very unstable towards bimolecular decomposition. Now, in the literature for the last couple of decades, people who have been interested in asymmetric at the metal species, and also in organic chemistry, where they talk about nonlinear effects in asymmetric reactions in organic chemistry. People are concerned with whether dimers are formed if they are homochiral or heterochiral, and what role that plays in terms of decomposition and so on in each of those cases. Now, we actually got a crystal structure of a methylene species in the process of decomposing and showed that it forms a species of this type before the carbon-carbon bond forms. And that is, the methylene behaves as a donor, like any donor, phosphine, olefin, whatever, toward the carbon, nitrogen, oxygen face, just as I've been talking about. And so the dimer that would decompose to give ethylene in a chiral case that I've been talking about, this is the homochiral version, would look like that. And what we're thinking is that the homochiral version of these asymmetric at the metal species, if this alkoxide is extremely large, probably can't form as easily as the heterochiral version, where the alkoxide and that amido group are switched. So one alkoxide would be over here, the other one would be over here. That decomposition could be faster than this one, where the dimer may not even be able to form. So preservation of the methylene and any other alkylidine during the reaction, because the metal is chiral and because the bimolecular pathway now is slowed down or blocked, may be very, very important in keeping these catalysts turning over and for overall leading to very fast reactions. So there aren't many examples in the literature. In fact, I don't know of any other example of a metal complex with 4 different ligands on it that is either diastereomerically pure or enantiomerically pure or some mixture or anything that gives rise to a nice asymmetric reaction of any sort. This, in fact, may be the only example, or these that I'm talking about, and they are the only examples involving metal complexes with 4 different unconnected ligands, A, B, C, D. Of course, you're using one of those, that's a metathesis reaction, replacing it with another, and in fact, if you go through the mechanism, that results in inversion at the metal center. So there's some very, very interesting fundamental questions involved, mechanistic questions in this chemistry. Everything, practically everything out there in terms of asymmetric reactions involves bidentate ligands. And there's nothing, very few that involve monodentate ligands, and nothing that I could find involving a monodentate chiral auxiliary as a means of establishing chirality in an asymmetric reaction. I mentioned what Odile Eisenstein is thinking about, certainly electronic control at the metal center. Chirality at the metal center is probably the most efficient way to use chirality or to do reactions asymmetrically. This is interesting. Because these reactions are long-lived, apparently, and because they're long-lived, or they're long-lived because of chirality at the metal, perhaps they could be useful for a lot of other reactions where asymmetric is not the object, simply longevity and turnover number. So you can use asymmetric catalysts for symmetric reactions simply because they're very long-lived and very reactive. And I mentioned the homochiral versus heterochiral. Okay, I wanted to finish up then with a couple of areas, or give you some idea of what's happening in terms of metathesis. And this is one I thought you might be interested in, and that is alkane metathesis. So this is basically some sort of high temperature, what you would call a reforming type reaction, where you turn one alkane into a mixture of alkanes. Could you imagine chopping a carbon-carbon single bond randomly and yielding a distribution of alkanes starting with one alkane? That is, upgrading alkanes from a lighter alkane like hexane, and we heard about this in the talk yesterday. Sometimes it would be nice if you could take a small alkane and turn it into an alkane twice the size, or roughly upgrade it to a longer, higher boiling product. This is a process that was actually discovered about 20 years ago, I believe, in the early 60s. Jean-Marie Basset's lab also discovered a version a few years ago. And then more recently, Maurice Burckhardt and Alan Goldman discovered a way to carry out this bizarre alkane metathesis reaction. And it's ironic that in order to carry out the alkane metathesis reaction, you have to create a bond that is stronger than a single bond. You have to create a double bond. So what happens is you use a catalyst based on iridium to remove hydrogen from an alkane to give a tiny amount of an alkene. I show it selectively in the terminal position here, but it could be anywhere. You'd like it to be selective in the terminal position. And then that's an equilibrium, of course, and then you use a metathesis catalyst to metathesize any alkenes that are present. In this case, it would yield ethylene and 5-decene. That's all reversible. So if the reaction were perfectly selective, you would get from hexane, you would get a mixture of ethane and decane. These reactions actually work. They are one of the very rare, what you would call tandem reactions or dual reactions. One catalyst performing one role, another catalyst performing another. Obviously, they can't interfere with one another, and in fact, apparently they do not in this particular case. So for octane, a typical number of turnovers is, let's say, 2,000, so it's impressive, but not going to win any prizes. It's slow. These are some of the disadvantages. Very slow reaction. Temperatures are about 125 degrees, which is maybe hot by homogeneous standards, but quite cold by heterogeneous standards. Of course, it involves iridium, which is fairly costly, and it's not selective, as I showed here. You don't get a mixture from hexane of ethane and decane. In fact, you get all alkanes. So this is a typical chromatogram starting with octane and throwing in the iridium catalyst. These are both homogeneous in the pot, catalysts in the pot together. And in this case, this tungsten perfluorotebutoxide, bis perfluorotebutoxide catalyst. And after 4 days at 125 degrees, you see a distribution of alkanes, both high and low. No methane because there's no mechanism for forming methane. So the smallest, not olefin alkanes, the smallest alkane is ethane, and that's mostly evolved in this workup, so you don't see it, but it is there. So we've been working, trying to, in a collaboration then with Goldman and Burckhardt, established what metathesis catalysts might be better than the standard one, and the standard one was the molybdenum bis hexafluorotebutoxide. And that's shown here in terms of some sort of turnover number and or concentration. Bis hexafluorotebutoxide, you probably can't read this, but that's what this bar is. The tungsten bis hexafluorotebutoxide gives quite a few more turnovers, 30% or so. And the non-fluoro or perfluorotebutoxide of tungsten, again, a few more, about 50% more than the molybdenum species. But in general, it looks like, at least in these alkane metathesis reactions, tungsten is better. Interestingly, the tungsten mono F6 monopyrrolide, one of these that I've been talking about that I say is supposed to be very reactive and relatively stable, does not outperform the bis alkoxides yet, but it certainly is up there in that same category. So here's the tungsten mono F6 monopyrrolide. Molybdenum species in general are not as successful, and imido groups smaller than 2,6-disopropyl imido, like adamantyl groups or ortho-CF3 phenyl groups on the molybdenum imido ligand, perform poorly compared to diisopropyl phenyl containing species. So we're still looking extensively, but it's slow going. These results are not easy to obtain. Each of these results takes about a week to get, and so it's rather tedious. Most of you are interested in heterogeneous catalysis. And of course, if you know enough about a homogeneous catalyst, you can prepare on the surface from that homogeneous catalyst something that essentially is the same, except it's bound to the surface. And this is what is being done largely at Lyon by Basset and his co-workers. And these bispyralides are exactly poised for putting on surfaces, because on a surface in which the hydroxyl groups on a silica that's been heated to 700 degrees, these hydroxyl groups on the average are about 10 angstroms apart. This is a fumed silica sold by Degussa. And if you add the bispyralide, by definition, you cannot then get a bissiloxide. You monoattach these species, and you make the very type of MAP species that I've been talking about, where the alkoxide is now a siloxide bound to the surface. So this has been proven through mainly NMR techniques that these are the type of species that are formed. And of course, we can't detect different structures. They are presumably racemic. There's nothing chiral here. But in the future, we might want to have a chiral auxiliary present and make diastereomers on the surface. But the main message is, obviously, on a homogeneous or heterogeneous surface, you're not going to decompose intermediates, even methylenes, because they are not close enough to combine. And so for that reason, presumably, you get very high turnovers. So these are very, very reactive compared to their homogeneous analog. Roughly 200,000 turnovers for propylene, in this case at an initial rate of 600 turnovers a minute, 10 per second. And so that's very fast. You cannot do this with the homogeneous alkoxide or siloxide analog. These catalysts don't last forever because metallocycles do rearrange to olefins, and so they do, in fact, die, presumably for that reason, eventually, but only after a very high number of turnovers have been carried out. So this was published earlier in 2007 in collaboration with the Basset group. I think in view of the time, I won't talk to you about the third new result, and that is a ring opening of substituted cyclopropenes. Again, you would think that would be a reaction that's been known for a long time, but in fact, this is the first example of ring opening of 3,3-disubstituted cyclopropenes. They're all trans, a lot of interesting tacticity issues, but because of the time constraints, I think I'll stop there and move ahead to the acknowledgement slides. You can control that tacticity again by controlling the nature of the alkoxide. I don't know if I'm doing this or the people in the back are doing this. Well, there's the message, the penultimate slide, variations of the answer. But now we have thousands, or maybe even tens of thousands, depending how you want to count it, of possibilities. If you count the metal, molybdenum or tungsten, imido groups, 10 alkoxides, either chiral or not. Who knows how big that number is, 100. Pyralides, very easy to make pyralides. Different pyralides behave differently, chiral or not. We don't have any chiral examples, but that is also variable. The alkylidines are variable, of course. You can support it or not support it, so on. Thousands of variations are possible. So this is going to require a lot of combinatorial or rapid throughput techniques in order to evaluate which catalyst is going to be useful in a given situation. And that's where somebody like Symix is going to come in with their techniques, combinatorial techniques, to evaluate catalysts just of this in this sort of situation. Okay, well that's it. Here are the acknowledgments. The National Science Foundation has supported me for many years. NIH has supported me for asymmetric metathesis and also for dinitrogen reduction. I've mentioned Amir Hoveda and his group at Boston College, invaluable in this collaboration that's been going on for about 10 years and has produced about 35 papers. And now, as I mentioned, I'm collaborating with just one postdoc with Burkhardt and Goldman in this very interesting new Alkane Metathesis reaction. Here are some of the people who've done some of the work that I talked about. And with that, I want to thank them, and I want to thank you, and I want to thank the organizers again for the invitation to be here. Thank you very much, all of you.
Thank you very much for your excellent talk. And on behalf of the organizing committee, we would like to present a little souvenir for you.